Thank you for attending this session. So we're going to go into a little bit deeper into nonlinear programming problems. You have the original video, but this will give you two more demonstrations on how to implement nonlinear programming. The first example that we would like to try comes from a page in our course notes on linear programming. So you can look in our course notes and we have a graphical illustration of a nonlinear programming problem. We see the formulation here on the left side. We see the formulation there. We can then, here is the objective function, 3x1 plus 5x2. We want to maximize that. x1 is less than or equal to 4. That's shown right here. 9 x1 squared plus 5 x squared 2 is less than or equal to 216. That's represented by this curved line right here. So because it's a curved line, we're now dealing with nonlinear programming. Because of the x1 squared and the x2 squared, this becomes a nonlinear programming. The objective function is still a straight line, but the feasible region now has a curved area that makes this a nonlinear programming problem. So let's go out here then and let's solve this as a nonlinear programming problem. So you can see down here, I've set up our matrix again. So the x1 coefficient, and we're looking here at the objective function. We want to maximize that. 3 times x1 plus 5 times x2. So here's the 3, the coefficient of 3 for x1. x1 will set that equal to 1 initially. 5 times x2. Here's the 5, the coefficient for x2 in the objective function will initially set x2 equal to 1. Constraint number 1, x1 is less than or equal to 4. So the coefficient for x1 is equal to 1. And again, here, because we're cell referencing, that's going to be equal to x1 in the top cell, which is, in this case, it's E24. There's no x2. Therefore, the coefficient for x2 is 0. We'll still set the x2 equal to the value of the x2 in the top cell, which is G24. And again, practice good programming and cell reference. For constraint number 2, this is going to be 9x1 squared. So the coefficient is 9. We'll set x1 equal to 1. And then for x2, it's 5 x2 squared. So the coefficient is equal to 5. And again, we're cell referencing. So at this point, cell G26 is equal to cell G24. we have the constraints, the limits, the upper limits for both constraints number 1 and number 2. So you see right here that the upper limit for constraint number 1 is 4. So we've listed that here. The upper limit for constraint number 2 is equal to 216. And so we have that listed here. On the equations for the objective function and the constraints, they're all going to be the same equation. So you can see here, then that's going to be for the objective function, D24 times E24 plus F24 times G24. Right now, that's equal to 8, and that makes sense because that's just equal to 3 times 1 plus 5 times 1, that's equal to 8. For the first constraint, I just copied the equation from the objective function into constraint number 1. We know that the second part, F25 is equal to 0, so everything within this parentheses is equal to 0. But for x1, right now we have 1 times 1. D25 is equal to 1. E25 is equal to 1. 1 times 1 plus 0. And that's going to give us 1. Again, the upper constraint for constraint number 1 is going to be equal to 4. For constraint number 2, now this is going to, the programming for this is going to be a little bit different. So this is going to be for x1, it's going to be 9 times x1 squared. So if we look at the equation, this is equal to left parentheses D26 times x1, which is an E26 squared. Right parentheses, plus left parentheses 5. That's in cell F26 times left parentheses G26, which currently has a value of 5, times left parentheses G26 squared. G26 currently has a value of 1, right parentheses. So right now it's going to be 9 times 1 plus 5 times 1. 9 plus 5 is equal to 14. So it looks like the equation in cell I26 is correct. And remember that the upper constraint for upper value for constraint number 2 is 216. That's just given to us in the formulation. Now, let's run the solver command to determine what the optimal values for x1 and x2 are, and what is the optimal value we can get from this nonlinear programming. We'll see that in our objective. So data, solver, we want to set the objective function, and that's going to be in cell I24. We want to set that to a maximum by changing which cells? X1, so this is going to be E24, and X2, which is going to be G24. So we want to change E24 and G24. Let's add the constraints now. So I want to add constraint number 1. The result is going to be in cell I25. That has to be less than or equal to 4. So here is the less than or equal to sign there. The constraint is 4. So constraint number 1 must be less than or equal to 4. Let's add constraint number 2. So constraint number 2 is in cell I26. That has to be, you see from our formulation, less than or equal to 216. So the dialog box then for this simple nonlinear programming is set up. Let's hit OK. Let's make the unconstrained variables non-negative. And again now, this is a nonlinear programming, so we can't use the simplex. So let's go with GRG nonlinear. You can see that the dialog box looks like it's complete now. Looks like it's complete. So let's hit solve. Let's hit solve. And let's hit OK. So X1, according to solver, is 1.999, which is close enough to 2. X2 is 6.000517, close enough to 6. So we can just really make this 2 and 6. The result that we come up with is equal to 36. So let's look at the original problem. Let me make this a little bit bigger. So we have X1 is equal to 2, X2 is equal to 6, and the value with X1 equal to 2 and X2 equal to 6, the value of the objective function is equal to 36. So let's make this a little bit bigger. A little bit more. And you can see then in the original problem, in the graph, right here, they're showing the optimal solution. X1 is equal to 2, X2 is equal to 6. That's what we got down here. We were able to replicate those results. And we see right here that the value of the objective function is 36. And again, we see in the original problem a value of the objective function z is equal to 36. We used the solver command in Excel to replicate the results that were given to us in this problem. So again, the solver command in Excel was able to derive the correct results. The answers shown in our class notes is x1 is equal to 2, x2 is equal to 6. Here's x1, x2, little bit off, but boy, just a little bit. Basically, we were able to derive the correct answer. So we see then that the solver in Excel is robust, and we're able to replicate the results that we have in our class notes. Let's look at another problem now. So I have another problem here. And let me make this a little bit bigger. So I've done a lot of this for the sake of saving some time here. And now this is the inputs into a software, a mathematical programming software that is specifically tailored towards mathematical programming problems. We know that Excel does a lot, accounting, statistics, but this software that we're generating here, that we're looking at here, is specifically for mathematical programming problems. So this is the way you input these type of problems into this mathematical programming. And so let me try to interpret this for you. I'll go from here left to right. Here is the objective function. We want to minimize then x1 times x4 times left parentheses x1 plus x2 plus x3 right parentheses plus x3. And you can see that here. I type this in, minimize x1 times x4 times left parentheses x1 plus x2 plus x3 right parentheses plus x3. That's the objective function. Constraint number 1, x1 times x2 times x3 times x4 is greater than or equal to 25. You see that right here? x1 times x2 times x3 times x4 is greater than or equal to 25. And the second constraint then, and again written in the format required for this particular software, x1 squared plus x2 squared plus x3 squared plus x4 squared is equal to 40. Is equal to 40. So x1 squared plus x2 squared plus x3 squared plus x4 squared is equal to 40. Equal to 40. And we have a lot more of these constraints now. And that's coming from this portion. So x1. X1 here, you could see here, x1 has to be greater than or equal to 1, and x1 has to be less than or equal to 5. You see that right here. X2 has to be greater than or equal to 1, less than or equal to 5. X3 greater than or equal to 1, less than or equal to 5. You could see that right here. And then finally, right here, X1 is greater than or equal to 1. X4 is less than or equal to 5. X4 is less than or equal to 5. So basically, for X1, X2, X3, and X4, all of them are bounded. It has to be greater than or less, greater than or equal to 1, and less than or equal to 5. So this mathematical programming that we have here, you could see that we have the objective function, but now we have a lot of constraints. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 constraints for this minimization problem. This is the formulation. This is the formulation. It takes a little training to see the formulation from here. Formulation from here. So right here, here's the objective function. Here's part of the formulation. Also, you see right here, here's additional constraints that must be put into the formulation. These are the commands. These are the commands that you must enter into this software. So it takes a little training to use this software. We can use Excel, however, and you'll see that we're going to get good results also. So down here then, and let's just set these up now. 1, 1, 1. Here's the objective function. That's right here. X1 times X4 times left parentheses, X1 plus X2 plus X3, right plus 3. I programmed this in, but you can see the programming to get that result on the objective function. And for constraint number 1, that's going to be equal to X1 times X2 times X3 times X4. That has to be greater than 25. Here's constraint number 2. The minimum of constraint number 2 has to be greater than 25. Then for constraint number 2, we have X1 squared plus X2 squared plus X3 squared plus X4 squared has to be equal to 40. Equal to 40. And now all these constraints, these additional constraints, really didn't have to do this before. But these constraints down here, X1 is greater than or equal to 1, X1 is less than or equal to 5. X2, same story. You see the upper limits that we set for X1 through X4 all are here. x1, x2, x3, x4, all must be greater than or equal to 1, less than or equal to 5. So there's a lot of programming that's involved to make sure that these constraints follow the formulation. So there's the setup that we need to insert into solver command for Excel. So this is a minimization problem. Remember, this is a minimization problem. And again, here is as close as I can get to the algebraic form of the formulation. So x1 times x4 times left parentheses x1 plus x2 plus x3, right, plus 3. We want to minimize this objective function. Constraint number 1, x1 times x2 times x3 times x4 is greater than or equal to 25. X1 squared plus x2 squared plus x3 squared plus x4 squared is equal to 40. Equal to 40. And for all of these, again, x1, x2, x3, x4 must be greater than or equal to 1, less than or equal to 5. There are all of our constraints. Now, let me do this. So, data, solver. You could see then that I already did the inputs into the solver command because it takes such a long time. It takes such a long time. And so I put the objective function. We want to minimize the objective function by changing cells x1, x2, x3, x4. All of these are the constraints. And you could see right here, I'm sorry, that's difficult to see. But you can see then that cell I-23 has to be equal to 40. Equal to. Not less than or equal to or greater than or equal to. In this mathematical programming problem, it has to be equal to 40. And J22, so that's down here. That's down here. I-22, this cell here, has to be greater than or equal to 25. So I-23, this is constraint number 2. I-23 is constraint number 2. I-22 is constraint 21. I entered all of these in because it's tedious and just for the sake of time. You know how to do this already. We want to make x1, x2, x3, x4 non-negative. And again, we have a choice. We can do GRG nonlinear. Remember that the simplex is for linear programming. Evolutionary, we could have used that too, but let's go with GRG nonlinear. I think everything is okay now. So let's hit solve. We hit okay. So for this nonlinear programming problem, given the objective function and given the constraints, x1 is equal to 1. x2 is equal to 4.74. X3 is equal to 3.82. X4 is equal to 1.38. This is going to give us a value of the objective function of 17.014. The value for constraint number 1 is 25. Again, constraint number 1 had to be greater than or equal to 25. Constraint number 2 had to be equal to 40. Here's the results. Here's the constraints. And again, x1 had to be greater than or equal to 1. x1 had to be less than or equal to 5. We meet that. x2 greater than or equal to 1. Yes. Less than or equal to 5. Yes. x3 greater than or equal to 1. Yes. Less than or equal to 5. Yes. x4 greater than or equal to 1. Yes. Less than or equal to 5. Yes. So these are, for this nonlinear programming, these are the optimal values for x1, x2, x3, x4. Now, this was originally run in this advanced software. And this software, I think, is specifically made for mathematical programming only. It's not flexible like Excel. Okay, so again, here are the values for x1, x2, x3, x4. Let's see what the advanced software, what their answers were. So we have the objective value. The advanced software came with 17.014, just like ours. The advanced software right here, you can see x1 is equal to 1. That's what we came up with. The advanced software says x2 is equal to 4.743. You can see that right here. 4.743. x3, 3.821. Again, right there. And x4, 1.379. So again, we're right there. So Excel was able to replicate the results of this advanced software. Again, this advanced software is dedicated to mathematical programming problems only. However, using the solver command in Excel, we were able to duplicate the results from the advanced software. Hopefully, this is some proof of the power of the solver function in Microsoft Excel. So these were then two demonstrations. Here was example number 1. We got the right answer for the nonlinear programming. Here's example number 2. Again, we were able to derive the correct results for this nonlinear programming problem. We had two demonstrations of nonlinear programming. That concludes this presentation of 2 examples of nonlinear programming. Thank you very much. Thank you for watching, and this concludes this video. Thank you again.